Boron, Wikipedia article audio. Boron is a chemical element with symbol B and atomic number 5. Produced entirely by cosmic ray spallation and supernovae and not by stellar nucleosynthesis, it is a low-abundance element in the Solar System and in the Earth's crust. Boron is concentrated on Earth by the water solubility of its more common naturally occurring compounds, the borate minerals. These are mined industrially as evaporites, such as borax and kernite. The largest known boron deposits are in Turkey, the largest producer of boron minerals. Elemental boron is a metalloid that is found in small amounts in meteoroids, but chemically uncombined boron is not otherwise found naturally on Earth. Industrially, very pure boron is produced with difficulty because of refractory contamination by carbon or other elements. Several allotropes of boron exist. Amorphous boron is a brown powder, crystalline boron is silvery to black, extremely hard, and a poor electrical conductor at room temperature. The primary use of elemental boron is as boron filaments, with applications similar to carbon fibers in some high-strength materials. History. Preparation of elemental boron in the laboratory. Boron is primarily used in chemical compounds. About half of all boron consumed globally is an additive in fiberglass for insulation and structural materials. The next leading use is in polymers and ceramics in high-strength, lightweight structural, and refractory materials. Borosilicate glass is desired for its greater strength and thermal shock resistance than ordinary soda-lime glass. Boron compounds are used as fertilizers in agriculture and in sodium perborate bleaches. A small amount of boron is used as a dopant in semiconductors, and reagent intermediates in the synthesis of organic fine chemicals. A few boron-containing organic pharmaceuticals are used or are in study. Natural boron is composed of two stable isotopes, one of which has a number of uses as a neutron-capturing agent. In biology, borates have low toxicity in mammals, but are more toxic to arthropods and are used as insecticides. Boric acid is mildly antimicrobial, and several natural boron-containing organic antibiotics are known. Boron compounds play a strengthening role in the cell walls of all plants, making boron a necessary plant nutrient. There is no consensus on whether boron is an essential nutrient for mammals, including humans, although there is some evidence it supports bone health. The word boron was coined from borax, the mineral from which it was isolated, by analogy with carbon, which boron resembles chemically. Borax, its mineral form then known as tincal, glazes were used in China from AD 300, and some crude borax reached the West, where the Perso-Arab alchemist Jabir ibn Hayyan apparently mentioned it in AD 700. Marco Polo brought some glazes back to Italy in the 13th century. Agricola, around 1600, reports the use of borax as a flux in metallurgy. In 1777, boric acid was recognized in the hot springs near Florence, Italy, and became known as sal sedativum, with primarily medical uses. The rare mineral is called sassolite, which is found at Sasso, Italy. Sasso was the main source of European borax from 1827 to 1872, when American sources replaced it. Boron compounds were relatively rarely used until the late 1800s, when Francis Marion Smith's Pacific Coast Borax Company first popularized and produced them in volume at low cost. Boron was not recognized as an element until it was isolated by Sir Humphrey Davy and by Joseph Louis Gay-Lussac and Louis Jacques Thénard. In 1808 Davy observed that electric current sent through a solution of borates produced a brown precipitate on one of the electrodes. In his subsequent experiments, he used potassium to reduce boric acid instead of electrolysis. He produced enough boron to confirm a new element and named the element boricium. Gay-Lussac and Thénard used iron to reduce boric acid at high temperatures. By oxidizing boron with air, they showed that boric acid is an oxidation product of boron. Jöns Jacob Berzelius identified boron as an element in 1824. Pure boron was arguably first produced by the American chemist Ezekiel Weintraub in 1909. Characteristics. The earliest routes to elemental boron involved the reduction of boric oxide with metals such as magnesium or aluminium. However, the product is almost always contaminated with borides of those metals. Pure boron can be prepared by reducing volatile boron halides with hydrogen at high temperatures. Ultra-pure boron for use in the semiconductor industry is produced by the decomposition of diborane at high temperatures and then further purified with the zone melting or Czochralski processes. The production of boron compounds does not involve the formation of elemental boron, but exploits the convenient availability of borates. Allotropes. Boron is similar to carbon in its capability to form stable covalently bonded molecular networks. Even nominally disordered boron contains regular boron icosahedra which are, however, bonded randomly to each other without long-range order. Crystalline boron is a very hard, black material with a melting point of above 2000 degrees Celsius. It forms four major polymorphs, alpha-rhombohedral and beta-rhombohedral, gamma and beta-tetragonal. Alpha-tetragonal phase also exists, but is very difficult to produce without significant contamination. Most of the phases are based on B12 icosahedra, but the gamma phase can be described as a rock salt type arrangement of the icosahedra and B2 atomic pairs. It can be produced by compressing other boron phases to 1220 GPa and heating to 1500–1800 degrees C. It remains stable after releasing the temperature and pressure. The T phase is produced at similar pressures, but higher temperatures of 1800–2200 degrees C. As to the alpha and beta phases, they might both coexist at ambient conditions with the beta phase being more stable. Compressing boron above 160 GPa produces a boron phase with an as yet unknown structure, and this phase is a superconductor at temperatures 612 K. Borosphyrine molecules and boraphenine have been described in 2014. Elemental boron is rare and poorly studied because the pure material is extremely difficult to prepare. Most studies of boron involve samples that contain small amounts of carbon. The chemical behavior of boron resembles that of silicon more than aluminium. Crystalline boron is chemically inert and resistant to attack by boiling hydrofluoric or hydrochloric acid. When finely divided, it is attacked slowly by hot concentrated hydrogen peroxide, hot concentrated nitric acid, hot sulfuric acid or hot mixture of sulfuric and chromic acids. The rate of oxidation of boron depends on the crystallinity, particle size, purity, and temperature. Boron does not react with air at room temperature, but at higher temperatures it burns to form boron trioxide. Chemistry of the element. Boron undergoes halogenation to give trihalides, for example. Chemical compounds. The trichloride in practice is usually made from the oxide. Organoboron chemistry. In the most familiar compounds, boron has the formal oxidation state 3. These include oxides, sulfides, nitrides, and halides. The trihalides adopt a planar trigonal structure. These compounds are Lewis acids in that they readily form adducts with electron pair donors, which are called Lewis bases. For example, fluoride and boron trifluoride combine to give the tetrafluoroborate anion, BF4. Boron trifluoride is used in the petrochemical industry as a catalyst. The halides react with water to form boric acid. Compounds of B and B. Boron is found in nature on Earth almost entirely as various oxides of B, often associated with other elements. More than 100 borate minerals contain boron in oxidation state +3. These minerals resemble silicates in some respect, although boron is often found not only in a tetrahedral coordination with oxygen, but also in a trigonal planar configuration. Unlike silicates, the boron minerals never contain boron with coordination number greater than 4. A typical motif is exemplified by the tetraborate anions of the common mineral borax, shown at left. The formal negative charge of the tetrahedral borate center is balanced by metal cations in the minerals, such as the sodium in borax. A very important boron-bearing mineral group is also the tourmaline group of borate silicates, and quite a lot of borosilicates is also known to exist naturally. Boranes are chemical compounds of boron and hydrogen, with the generic formula of BXHY. These compounds do not occur in nature. Many of the boranes readily oxidize on contact with air, some violently. The parent member BH3 is called borane, but it is known only in the gaseous state, and dimerizes to form diborane, B2H6. The larger boranes all consist of boron clusters that are polyhedral, some of which exist as isomers. For example, isomers of B20H26 are based on the fusion of two 10-atom clusters. The most important boranes are diborane B2H6 and two of its pyrolysis products, pentaborane B5H9 and decaborane B10H14. A large number of anionic boron hydrides are known, e.g. 2. The formal oxidation number in boranes is positive, and is based on the assumption that hydrogen is counted as one as in active metal hydrides. The mean oxidation number for the borons is then simply the ratio of hydrogen to boron in the molecule. For example, in diborane B2H6, the boron oxidation state is +3, but in decaborane B10H14, it is 7/5 or +1.4. In these compounds the oxidation state of boron is often not a whole number. The boron nitrides are notable for the variety of structures that they adopt. They exhibit structures analogous to various allotropes of carbon, including graphite, diamond, and nanotubes. In the diamond-like structure, called cubic boron nitride, boron atoms exist in the tetrahedral structure of carbon's atoms in diamond, but 1 in every 4 Bn bonds can be viewed as a coordinate covalent bond, wherein 2 electrons are donated by the nitrogen atom which acts as the Lewis base to a bond to the Lewis acidic boron center. Cubic boron nitride, among other applications, is used as an abrasive, as it has a hardness comparable with diamond. In the Bn compound analog of graphite, hexagonal boron nitride, the positively charged boron and negatively charged nitrogen atoms in each plane lie adjacent to the oppositely charged atom in the next plane. Consequently, Graphite and HBN have very different properties, although both are lubricants, as these planes slip past each other easily. However, HBN is a relatively poor electrical and thermal conductor in the planar directions. Isotopes. A large number of organoboron compounds are known and many are useful in organic synthesis. Many are produced from hydroboration, which employs diborane, B2H6, a simple borane chemical. Organoboron compounds are usually tetrahedral or trigonal planar, for example, tetraphenyl borate, 4 versus triphenyl borane, B3. However, multiple boron atoms reacting with each other have a tendency to form novel dodecahedral and icosahedral structures composed completely of boron atoms, or with varying numbers of carbon heteroatoms. Commercial isotope enrichment. Organoboron chemicals have been employed in uses as diverse as boron carbide, a complex very hard ceramic composed of boron-carbon cluster anions and cations, to carborons, carbon-boron cluster chemistry compounds that can be halogenated to form reactive structures including carboron A acid, a superacid. As one example, carborons form useful molecular moieties that add considerable amounts of boron to other biochemicals in order to synthesize boron-containing compounds for boron neutron capture therapy for cancer. A number of potential boronet pharmaceuticals using boron-10 have been prepared for use in boron neutron capture therapy. Some boron compounds show promise in treating arthritis, though none have as yet been generally approved for the purpose. Although these are not found on Earth naturally, boron forms a variety of stable compounds with formal oxidation state less than 3. As for many covalent compounds, formal oxidation states are often of little meaning in boron hydrides and metal borides. The halides also form derivatives of B and BBF, isoelectronic with N2, cannot be isolated in condensed form, but B2F4 and B4Cl4 are well characterized. Binary metal boron compounds, the metal borides, contain boron in negative oxidation states. Illustrative is magnesium diboride. Each boron atom has a formal 1 charge and magnesium is assigned a formal charge of +2. In this material, the boron centers are trigonal planar with an extra double bond for each boron, forming sheets akin to the carbon in graphite. However, unlike hexagonal boron nitride, which lacks electrons in the plane of the covalent atoms, the delocalized electrons in magnesium diboride allow it to conduct electricity similar to isoelectronic graphite. In 2001, this material was found to be a high-temperature superconductor. Certain other metal borides find specialized applications as hard materials for cutting tools. Often the boron in borides has fractional oxidation states, such as 1/3 in calcium hexaboride. Enriched boron. Depleted boron. Radiation-hardened semiconductors. Proton-boron fusion. From the structural perspective, the most distinctive chemical compounds of boron are the hydrides. Included in this series are the cluster compounds dodecaborate, decaborane, and the carborons such as C2B10H12. Characteristically, such compounds contain boron with coordination numbers greater than 4. Boron has 2 naturally occurring and stable isotopes, 11B and 10B. The mass difference results in a wide range of delta 11B values, which are defined as a fractional difference between the 11B and 10B and traditionally expressed in parts per thousand, in natural waters ranging from 16 to plus 59. There are 13 known isotopes of boron. The shortest-lived isotope is 7b, which decays through proton emission and alpha decay. It has a half-life of 3.5 times 1022 s. Isotopic fractionation of boron is controlled by the exchange reactions of the boron species B3 and 4. Boron isotopes are also fractionated during mineral crystallization, during H2O phase changes in hydrothermal systems, and during hydrothermal alteration of rock. The latter effect results in preferential removal of the 4 ion onto clays. It results in solutions enriched in 11B3 and therefore may be responsible for the large 11B enrichment in seawater relative to both oceanic crust and continental crust. This difference may act as an isotopic signature. The exotic 17b exhibits a nuclear halo, i.e. its radius is appreciably larger than that predicted by the liquid drop model. The 10b isotope is useful for capturing thermal neutrons. The nuclear industry enriches natural boron to nearly pure 10b. The less valuable byproduct, depleted boron, is nearly pure 11b. Because of its high neutron cross-section, boron-10 is often used to control fission in nuclear reactors as a neutron-capturing substance. Several industrial-scale enrichment processes have been developed, however, only the fractionated vacuum distillation of the dimethyl ether adduct of boron trifluoride and column chromatography of borates are being used. Enriched boron or 10b is used in both radiation shielding and is the primary nuclide used in neutron capture therapy of cancer. In the latter, a compound containing 10b is incorporated into a pharmaceutical which is selectively taken up by a malignant tumor and tissues near it. The patient is then treated with a beam of low-energy neutrons at a relatively low neutron radiation dose. The neutrons, however, trigger energetic and short-range secondary alpha particle and lithium-7 heavy ion radiation that are products of the boron and neutron nuclear reaction, and this ion radiation additionally bombards the tumor, especially from inside the tumor cells. In nuclear reactors, 10b is used for reactivity control and in emergency shutdown systems. It can serve either function in the form of borosilicate control rods or as boric acid. In pressurized water reactors, boric acid is added to the reactor coolant when the plant is shut down for refueling. It is then slowly filtered out over many months as fissile material is used up and the fuel becomes less reactive. NMR spectroscopy. In future manned interplanetary spacecraft, 10b has a theoretical role as structural material which would also serve a special role in the radiation shield. One of the difficulties in dealing with cosmic rays, which are mostly high-energy protons, is that some secondary radiation from interaction of cosmic rays and spacecraft materials is high-energy spallation neutrons. Such neutrons can be moderated by materials high in light elements such as polyethylene, but the moderated neutrons continue to be a radiation hazard unless actively absorbed in the shielding. Among light elements that absorb thermal neutrons, 6Li and 10b appear as potential spacecraft structural materials which serve both for mechanical reinforcement and radiation protection. Cosmic radiation will produce secondary neutrons if it hits spacecraft structures. Those neutrons will be captured in 10b, if it is present in the spacecraft's semiconductors, producing a gamma ray, an alpha particle, and a lithium ion. Those resultant decay products may then irradiate nearby semiconductor chip structures, causing data loss. In radiation-hardened semiconductor designs, one countermeasure is to use depleted boron, which is greatly enriched in 11B and contains almost number 10B. This is useful because 11B is largely immune to radiation damage. Depleted boron is a byproduct of the nuclear industry. 11B is also a candidate as a fuel for aneutronic fusion. When struck by a proton with energy of about 500 keV, it produces 3 alpha particles and 8.7 MeV of energy. Most other fusion reactions involving hydrogen and helium produce penetrating neutron radiation, which weakens reactor structures and induces long-term radioactivity, thereby endangering operating personnel. However, the alpha particles from 11B fusion can be turned directly into electric power, and all radiation stops as soon as the reactor is turned off. Occurrence, production, market trend. Both 10B and 11B possess nuclear spin. The nuclear spin of 10B is 3 and that of 11B is 3/2. These isotopes are, therefore, of use in nuclear magnetic resonance spectroscopy, and spectrometers specially adapted to detecting the boron-11 nuclei are available commercially. The 10B and 11B nuclei also cause splitting in the resonances of attached nuclei. Boron is rare in the universe and solar system due to trace formation in the Big Bang and in stars. It is formed in minor amounts in cosmic ray spallation nucleosynthesis and may be found uncombined in cosmic dust and meteoroid materials. In the high oxygen environment of Earth, boron is always found fully oxidized to borate. Boron does not appear on Earth in elemental form. Extremely small traces of elemental boron were detected in lunar regolith. Although boron is a relatively rare element in the Earth's crust, representing only 0.001% of the crust mass, it can be highly concentrated by the action of water, in which many borates are soluble. It is found naturally combined in compounds such as borax and boric acid. About 100 borate minerals are known. On September 5, 2017, scientists reported that the Curiosity rover detected boron, an essential ingredient for life on Earth, on the planet Mars. Such a finding, along with previous discoveries that water may have been present on ancient Mars, further supports the possible early habitability of Gale crater on Mars. Applications. Economically important sources of boron are the minerals colemanite, rasorite, ulexite, and tincal. Together these constitute 90% of mined boron-containing ore. The largest global borax deposits known, many still untapped, are in central and western Turkey, including the provinces of Eskişehir, Kütahya, and Balıkesir. Global proven boron mineral mining reserves exceed 1 billion metric tons, against a yearly production of about 4 million tons. Turkey and the United States are the largest producers of boron products. Turkey produces about half of the global yearly demand, through ETI Mine Works, a Turkish state-owned mining and chemicals company focusing on boron products. It holds a government monopoly on the mining of borate minerals in Turkey, which possesses 72% of the world's known deposits. In 2012, it held a 47% share of production of global borate minerals, ahead of its main competitor, Rio Tinto Group. Almost a quarter of global boron production comes from the single Rio Tinto Borax mine 35°234.447 and 117°4045.412 W/35.04290194 degrees north 117.67928111 degrees west /35.04290194 117.67928111 near Boron, California. The average cost of crystalline boron is $5/g. Free boron is chiefly used in making boron fibers, where it is deposited by chemical vapor deposition on a tungsten core. Boron fibers are used in lightweight composite applications, such as high-strength tapes. This use is a very small fraction of total boron use. Boron is introduced into semiconductors as boron compounds, by ion implantation. Estimated global consumption of boron was about 4 million tons of B2O3 in 2012. Boron mining and refining capacities are considered to be adequate to meet expected levels of growth through the next decade. The form in which boron is consumed has changed in recent years. The use of ores like colemanite has declined following concerns over arsenic content. Consumers have moved toward the use of refined borates and boric acid that have a lower pollutant content. Increasing demand for boric acid has led a number of producers to invest in additional capacity. Turkey's state-owned ETI Mine Works opened a new boric acid plant with the production capacity of 100,000 tons per year at Emmet in 2003. Rio Tinto Group increased the capacity of its boron plant from 260,000 tons per year in 2003 to 310,000 tons per year by May 2005. With plans to grow this to 366,000 tons per year in 2006. Chinese boron producers have been unable to meet rapidly growing demand for high-quality borates. This has led to imports of sodium tetraborate growing by 100-fold between 2000 and 2005 and boric acid imports increasing by 28% per year over the same period. The rise in global demand has been driven by high growth rates in glass fiber, fiberglass, and borosilicate glassware production. A rapid increase in the manufacture of reinforcement-grade boron-containing fiberglass in Asia has offset the development of boron-free reinforcement-grade fiberglass in Europe and the USA. The recent rises in energy prices may lead to greater use of insulation-grade fiberglass, with consequent growth in the boron consumption. Reskill Consulting Group forecasts that world demand for boron will grow by 3.4% per year to reach 21 million tons by 2010. The highest growth in demand is expected to be in Asia, where demand could rise by an average 5.7% per year. Nearly all boron ore extracted from the earth is destined for refinement into boric acid and sodium tetraborate pentahydrate. In the United States, 70% of the boron is used for the production of glass and ceramics. The major global industrial-scale use of boron compounds is in production of glass fiber for boron-containing insulating and structural fiberglasses, especially in Asia. Boron is added to the glass as borax pentahydrate or boron oxide, to influence the strength or fluxing qualities of the glass fibers. Another 10% of global boron production is for borosilicate glass as used in high-strength glassware. About 15% of global boron is used in boron ceramics, including superhard materials discussed below. Agriculture consumes 11% of global boron production, and bleaches and detergents about 6%. Boron fibers are high strength, lightweight materials that are used chiefly for advanced aerospace structures as a component of composite materials, as well as limited production consumer and sporting goods such as golf clubs and fishing rods. The fibers can be produced by chemical vapor deposition of boron on a tungsten filament. Elemental boron fiber. Boronate fiberglass. Boron fibers and sub-millimeter-sized crystalline boron springs are produced by laser-assisted chemical vapor deposition. Translation of the focused laser beam allows production of even complex helical structures. Such structures show good mechanical properties and can be applied as reinforcement of ceramics or in micromechanical systems. Fiberglass is a fiber-reinforced polymer made of plastic reinforced by glass fibers, commonly woven into a mat. The glass fibers used in the material are made of various types of glass depending upon the fiberglass use. These glasses all contain silica or silicate, with varying amounts of oxides of calcium, magnesium, and sometimes boron. The boron is present as borosilicate, borax, or boron oxide, and is added to increase the strength of the glass, or as a fluxing agent to decrease the melting temperature of silica, which is too high to be easily worked in its pure form to make glass fibers. Borosilicate glass. The highly boronate glasses used in fiberglass are E-glass. E-glass is alumino-borosilicate glass with less than 1% W/W alkali oxides, mainly used for glass-reinforced plastics. Other common high boron glasses include C-glass, an alkali lime glass with high boron oxide content, used for glass staple fibers and insulation, and D-glass, a borosilicate glass, named for its low dielectric constant. Boron carbide ceramic. High hardness and abrasive compounds. Boron metal coatings. Detergent formulations and bleaching agents. Insecticides. Semiconductors. Magnets. Shielding and neutron absorber in nuclear reactors. Other non-medical uses. Pharmaceutical and biological applications. Research areas. Biological role. Analytical quantification. Health issues and toxicity. Not all fiberglasses contain boron, but on a global scale, most of the fiberglass used does contain it. Because the ubiquitous use of fiberglass in construction and insulation, boron-containing fiberglasses consume half the global production of boron, and are the single largest commercial boron market. Borosilicate glass, which is typically 12–15% B2O3, 80% SiO2, and 2% Al2O3, has a low coefficient of thermal expansion, giving it a good resistance to thermal shock. Schott AG's Duran and Owens Corning's trademarked Pyrex are two major brand names for this glass, used both in laboratory glassware and in consumer cookware and bakeware, chiefly for this resistance. Several boron compounds are known for their extreme hardness and toughness. Boron carbide is a ceramic material which is obtained by decomposing B2O3 with carbon in an electric furnace. Boron carbide's structure is only approximately B4C, and it shows a clear depletion of carbon from this suggested stoichiometric ratio. This is due to its very complex structure. The substance can be seen with empirical formula B12C3, but with less carbon, as the suggested C3 units are replaced with CBC chains, and some smaller octahedra are present as well. The repeating polymer plus semi-crystalline structure of boron carbide gives it great structural strength per weight. It is used in tank armor, bulletproof vests, and numerous other structural applications. Boron carbide's ability to absorb neutrons without forming long-lived radionuclides makes the material attractive as an absorbent for neutron radiation arising in nuclear power plants. Nuclear applications of boron carbide include shielding, control rods and shutdown pellets. Within control rods, boron carbide is often powdered, to increase its surface area. Boron carbide and cubic boron nitride powders are widely used as abrasives. Boron nitride is a material isoelectronic to carbon. Similar to carbon, it has both hexagonal and cubic forms. HBN is used as a high-temperature component and lubricant. CBN, also known under commercial name borazon, is a superior abrasive. Its hardness is only slightly smaller than, but its chemical stability is superior, to that of diamond. Heterodiamond is another diamond-like boron compound. Metal borides are used for coating tools through chemical vapor deposition or physical vapor deposition. Implantation of boron ions into metals and alloys, through ion implantation or ion beam deposition, results in a spectacular increase in surface resistance and microhardness. Laser alloying has also been successfully used for the same purpose. These borides are an alternative to diamond-coated tools, and their surfaces have similar properties to those of the bulk boride. For example, rhenium diboride can be produced at ambient pressures, but is rather expensive because of rhenium. The hardness of Reb2 exhibits considerable anisotropy because of its hexagonal layered structure. Its value is comparable to that of tungsten carbide, silicon carbide, titanium diboride, or zirconium diboride. Similarly, ALM14 plus TIB2 composites possess high hardness and wear resistance and are used in either bulk form or as coatings for components exposed to high temperatures and wear loads. Borax is used in various household laundry and cleaning products, including the 20 Mule Team Borax Laundry Booster and Boraxo Powdered Hand Soap. It is also present in some tooth bleaching formulas. Sodium perborate serves as a source of active oxygen in many detergents, laundry detergents, cleaning products, and laundry bleaches. However, despite its name, Borateam laundry bleach no longer contains any boron compounds, using sodium percarbonate instead as a bleaching agent. Boric acid is used as an insecticide, notably against ants, fleas, and cockroaches. Boron is a useful dopant for such semiconductors as silicon, germanium, and silicon carbide. Having one fewer valence electron than the host atom, it donates a hole resulting in p-type conductivity. Traditional method of introducing boron into semiconductors is via its atomic diffusion at high temperatures. This process uses either solid, liquid, or gaseous boron sources. However, after the 1970s, it was mostly replaced by ion implantation, which relies mostly on Bf3 as a boron source. Boron trichloride gas is also an important chemical in semiconductor industry, however not for doping but rather for plasma etching of metals and their oxides. Triethylborane is also injected into vapor deposition reactors as a boron source. Examples are the plasma deposition of boron-containing hard carbon films, silicon nitride boron nitride films, and for doping of diamond film with boron. Boron is a component of neodymium magnets, which are among the strongest type of permanent magnet. These magnets are found in a variety of electromechanical and electronic devices, such as magnetic resonance imaging, medical imaging systems, in compact and relatively small motors and actuators. As examples, computer HDDs, CD, and DVD players rely on neodymium magnet motors to deliver intense rotary power in a remarkably compact package. In mobile phones, neomagnets provide the magnetic field which allows tiny speakers to deliver appreciable audio power. Boron shielding is used as a control for nuclear reactors, taking advantage of its high cross-section for neutron capture. In pressurized water reactors, a variable concentration of boronic acid in the cooling water is used to compensate the variable reactivity of the fuel. When new rods are inserted, the concentration of boronic acid is maximal, and then reduced during the lifetime. Boric acid has antiseptic, antifungal, and antiviral properties, and for these reasons is applied as a water clarifier in swimming pool water treatment. Mild solutions of boric acid have been used as eye antiseptics. Bortezomib. Boron appears as an active element in its first approved organic pharmaceutical in the pharmaceutical bortezomib, a new class of drug called the proteasome inhibitors, which are active in myeloma and one form of lymphoma. The boron atom in bortezomib binds the catalytic site of the 20-SIXS proteasome with high affinity and specificity. Tavabarol is a aminoacyl tRNA synthetase inhibitor which is used to treat toenail fungus. It gained FDA approval in July 2014. Dioxyborolane chemistry enables radioactive fluoride labeling of antibodies or red blood cells, which allows for positron emission tomography imaging of cancer and hemorrhages, respectively. Magnesium diboride is an important superconducting material with the transition temperature of 39 kmgb. Wires are produced with the powder-in-tube process and applied in superconducting magnets. Amorphous boron is used as a melting point depressant in nickel-chromium brazed alloys. Hexagonal boron nitride forms atomically thin layers, which have been used to enhance the electron mobility in graphene devices. It also forms nanotubular structures, which have with high strength, high chemical stability, and high thermal conductivity, among its list of desirable properties. Boron is an essential plant nutrient, required primarily for maintaining the integrity of cell walls. However, high soil concentrations of greater than 1.0 ppm lead to marginal and tip necrosis in leaves as well as poor overall growth performance. Levels as low as 0.8 ppm produce these same symptoms in plants that are particularly sensitive to boron in the soil. Nearly all plants, even those somewhat tolerant of soil boron, will show at least some symptoms of boron toxicity when soil boron content is greater than 1.8 ppm. When this content exceeds 2.0 ppm, few plants will perform well and some may not survive. It is thought that boron plays several essential roles in animals, including humans, but the exact physiological role is poorly understood. A small human trial published in 1987 reported on postmenopausal women first made boron deficient and then replete with 3 mg/day. Boron supplementation markedly reduced urinary calcium excretion and elevated the serum concentrations of 17-beta-estradiol and testosterone. The U.S. Institute of Medicine has not confirmed that boron is an essential nutrient for humans, so neither a recommended dietary allowance nor an adequate intake have been established. Adult dietary intake is estimated at 0.9 to 1.4 mg/day, with about 90% absorbed. What is absorbed is mostly excreted in urine. The tolerable upper intake level for adults is 20 mg/day. In 2013, a hypothesis suggested it was possible that boron and molybdenum catalyzed the production of RNA on Mars, with life being transported to Earth via a meteorite around 3 billion years ago. There exist several known boron-containing natural antibiotics. The first one found was buromycin, isolated from Streptomyces. Congenital endothelial dystrophy type 2, a rare form of corneal dystrophy, is linked to mutations in SLC4A11 gene that encodes a transporter reportedly regulating the intracellular concentration of boron. For determination of boron content in food or materials, the colorimetric curcumin method is used. Boron is converted to boric acid or borates, and on reaction with curcumin in acidic solution, a red-colored boron chelate complex, rosocyanin, is formed. Elemental boron, boron oxide, boric acid, borates, and many organoboron compounds are relatively non-toxic to humans and animals. The LD50 for animals is about 6 grams per kg of body weight. Substances with LD50 above 2 grams are considered non-toxic. An intake of 4 g/day of boric acid was reported without incident, but more than this is considered toxic in more than a few doses. Intakes of more than 0.5 grams per day for 50 days cause minor digestive and other problems suggestive of toxicity. Single medical doses of 20 grams of boric acid for neutron capture therapy have been used without undue toxicity. Boric acid is more toxic to insects than to mammals, and is routinely used as an insecticide. The boranes and similar gaseous compounds are quite poisonous. As usual, it is not an element that is intrinsically poisonous, but their toxicity depends on structure. The boranes are also highly flammable and require special care when handling. Sodium borohydride presents a fire hazard owing to its reducing nature and the liberation of hydrogen on contact with acid. Boron halides are corrosive. Boron is necessary for plant growth, but an excess of boron is toxic to plants, and occurs particularly in acidic soil. It presents as a yellowing from the tip inwards of the oldest leaves and black spots in barley leaves, but it can be confused with other stresses such as magnesium deficiency in other plants.